Thank you. Hi, everyone. I see lots of familiar names on this list, so very interesting. Just a little bit of housekeeping. Could I remind everyone that it helps if you mute yourself? Click the mute button, otherwise it interrupts. So just leave me unmuted. Otherwise, when your phone rings or what have you, it interferes with things. Right. So as Claudia said, I'm the light relief here, really. This would have made more sense later in the week, but for this synchronized appearance with Claudia's lab seminar. So this is nothing to do with violins, except very generically. So let me now go to screen sharing. And I would like that, and I would like that, and go. So with a bit of luck. Are you seeing my screen? Yes, very good, thank you. So this is about the banjo. It's slightly more general than that. I'm interested, as you can see in this background picture here, there are lots of plucked instruments. You can see a lot of them hanging on the wall behind me in the little video image you have. So I got involved in a project to think about the banjo, and I will explain why in a moment, but let me just draw your attention to the strap line across the bottom of the screen here. Claudia will put this talk up available if you like, but there is already a version of this talk up on YouTube. So I gave one as our lab seminar a little while ago. So if you simply search for Woodhouse banjo on YouTube, you can drop onto this directly. So play the slideshow and get going. So I didn't do this project on my own, rather on the contrary, lots of people were involved. My main co-author was David Politzer. Here he is, as you see, with the banjo. Here he is being famous. This is him giving his Nobel Prize lecture. Needless to say, he didn't get the Nobel Prize for his work on the banjo. Lots of people were involved in this. Many of them are in the audience here. So there's some pictures of various people. Hossein Mansour did all the heavyweight computing. Here's Colin, you've just been listening to. There's all sorts of worthies of the musical acoustics world here. Claudia, a few years ago. Brian Moore is the great guru of psychoacoustics. He gave me some software for this. His fan, he's here, is Evan Davis, all sorts of people. Right, so back to this collection of instruments. Why am I interested in this question? Well, David is interested in this question because he's a banjo nut. So he wants to know about the banjo because he wants to know about the banjo. My interest is more complicated. As many of you know, I have a son who is a guitar maker. So I have I'm a plucked instrument person. So here's a whole bunch of plucked instruments, and they're different shapes. And I think if I asked any musician the question, do these instruments all sound different? They'd say, yes, of course they do. They would be quite sure that they could recognize any one of these 4 different instruments by listening to a little bit of the music. Well, I wonder if that's really true. Claudia, as she said, what she got us involved in doing more psychoacoustical work, and the essence of doing science about sounds we perceive and things we feel is that you don't believe anything in the folklore, you go in and do a test. So there's an interesting question here. Are we sure these instruments do sound different? Now, I'm really interested in, the answer, of course, is yes, up to a point. What is the point? I'm really interested in this question about what is it that gives different instruments their characteristic voice. Insofar as you can recognize these instruments, are some easier to recognize than others? If so, why? What's the key features? If we wanted to do a synthesis in the computer that was recognizable as a guitar or a harp, what would we have to do? If you're a maker making these instruments, it may be interesting. Well, now, instrument makers will have a different point of view from scientists on the next thing I'm going to say, but because instrument makers are always embedded in details. You're in there at the cutting edge, literally, you've got to think about every little shaving you take off the wood and so on. So violin makers are always very aware of arching shape and corners and F-holes and all the little details. Scientists, rather, as Colin alluded to, like to start from the other end. We want to start with doing the simplest things and then gradually work our way towards more complicated things. And the first rule of research, the first thing you have to tell any new research student is always do the easy things first. So if you want to approach this question of what gives these instruments their voice, can you recognize them? It pays to look at the most extreme example. And for reasons that will become clear in this talk, the banjo is the most extreme of all these instruments. With a bit of luck, if the audio comes through the internet all right, I will persuade you by the end that you can recognize the sound of a banjo, and roughly speaking, we do know why. Right, now this slide is a cue to me to stop sharing for a moment and just hold, and to quit out of the slideshow and just hold an instrument, whereupon I can't see myself. Sorry, let me just bring zoom back to that front window so I can see myself. Let me just talk through instruments a little bit. Here's a banjo. It's the one that most of this work was done on. Here's one of those other plucked instruments that was in the picture. Here's my lute. Now, roughly speaking, all plucked instruments work in the same way. You have stretched strings, and what the player does is you get hold of one of the strings, you pull it to one side, and you let go. The string vibrates, different strings, you change the length and so on. A vibrating string on its own is no good as a way of making sound. Just think about an electric guitar that's not plugged in. And the reason for that is simple. Strings are too small compared with the wavelength of sound. The air simply flows around a vibrating string. You don't make any pressure waves, you don't make any sound. So you need to do something to amplify it. If electric instruments, you can use electronics and loudspeakers. Acoustic instruments, we use a box, most often a wooden box. The banjo will be different, we'll come to that in a second. Sometimes we rather improperly talk about these boxes as mechanical amplifiers. Strictly speaking, that's misleading. There's no power source in the box. All the energy is created by the player plucking the string or by the violinist bowing the string. All the box is doing is making a more efficient way to turn some of that energy that you've put in into sound waves. The string itself is not very good at doing that, so it's a kind of impedance matcher. So all instruments work the same way. It's a kind of initial value problem. You pull the string to one side and you let go and you get a note. Now, nearly all of these instruments are wooden and are made by people rather like violin makers, just subtly different. The banjo really is different. The banjo, instead of using a wooden soundboard, is essentially a drum skin. That's one thing that's different. There's also a big difference of psychology because the player can do something which violin makers would think is horrifying, because the player can adjust almost everything about the instrument. They can change the tension of the head. Indeed, they can throw the head away and buy a new one and fit it. They can take the bridge off and change it and put a different one on. They can change the strings. Violinists can do that. But almost everything on the banjo is adjustable by the player in a way that we're really not used to in the wooden acoustic instruments. Now, let me put the slide back, but I'll just do a little bit more waffling before we get going. Now, back into screen share. Where is the Zoom window? Share screen. I want that one, and I still want that, and do it. Right, and then have the slideshow back. So, the banjo structure, what happens in a pluck. Now, what I'm going to talk about is going to come in 3 stages. This is classic kind of 19th century style of science. No quantum mechanics here. Indeed, there'll be no equations at all. I shall just do hand waving. There is lots of technical stuff in the background. You just have to believe me about that. We're going to do the classic 2 stages of science like they taught you at school. First, we're going to do some measurements, and then we're going to try to do a bit of modeling to understand the measurements. But this is about musical instruments, so we want to do the 3rd stage. It's not enough to have graphs in the computer and equations on the paper. We want to make noises and say, does it sound like it? So we're going to measure things about banjos. We're going to do a model of the banjo. And then I'm going to use that model to put together a computer simulation. And we will listen to them and say, well, does it sound like a banjo? Limited objectives, that's my last little cue point here. So what am I aiming to do in this study and this talk? The question of most interest is, can we nail this? Is it a banjo? Is it not a banjo? If I give you a plucked string note on different instruments, do you say, that one's a banjo? And then the answer to that, I hope to persuade you, is yes, we can do a reasonably good job on that. What I'm not going to do is address the question, the typical instrument maker's question, say, yes, that's any old banjo, but what about this particular banjo? Now, at this stage of the study, I'm not going to try to explain what makes one banjo different from another, or what can we recognize the sound of a particular banjo played by a particular player on a particular day. Interesting questions there, but we're not going to do it. It's much the same as what Colin was just talking about. He's talked about things essentially which all violins have in common to understand where those come from. It's a long way to go from there to say what makes this particular violin differ from that particular violin and why, and is that a good thing or not? Okay, so we start with measurements. Here's the simplest thing you can do. You can pluck a note on an instrument. We can grab it in a microphone, and we can turn it in the computer into a sonogram or a spectrogram, depending on who you are. So this is, I always plot things this way around. This is frequency running along the bottom and time running up here. And this is a plucked note. This top one is a plucked note on a guitar string. What are we seeing here? This stripy, fuzzy stripe across the bottom is the moment when I pluck the string. Time evolves upwards. What you see is this sort of fence of thin vertical lines. Those are the harmonics or almost harmonics of the sound, decaying away with time. You see them fading away. And then with some complicated stuff that I'll talk about in a moment at the bottom. So, as I said, I have a son who's a guitar maker, so I borrowed a steel string guitar from him. And very conveniently, the guitar he loaned me had a top string, which is essentially identical to the top string on this banjo. They're steel strings, same tension, same gauge. So what we've got here is the same note, the note G4. It's the 3rd fret on the top string of the guitar. It's the 5th fret on the top string of the banjo. That note there. So it's the same note being played on the same string. The only thing that's different is that one is attached to a wooden box and the other is attached to a drum. Do we see anything straight away? Well, what can we see? Superficially somewhat similar. They've all got these approximately harmonics. They're not quite exactly harmonic, but that's another story. If you look a little closely, one thing you can see straight away is that the banjo notes, that's the bottom picture, the banjo notes die away more quickly. Look at this frequency here. On the guitar, it's extending off the top of the graph. It's still going after 1.5 seconds. On the banjo, over the scale that I've plotted it, it's gone after 1 second. So looks as if the banjo note decays faster. Something you have to look very closely to see is that the banjo is louder. These two plots have got the same color scale. And if you look really carefully, you can see that there are brighter colors on the banjo. What the computer tells me is that the peak level in the guitar was about 10 dBs lower than the peak level in the banjo. I played them in a pretty similar way, sitting in the same place relative to the microphone and with a plectrum at the same place. So that's a first little view of things. I just want to draw one more thing to your attention down here. I've said All these vertical lines here are the harmonics of the string. But if you look closely, there are some other vertical lines. You see for the guitar right down at low frequencies, you can see a few other little vertical stripes dying away rather quickly. And those are body modes of the instrument. They're the things Colin was talking about. We have a wooden box. I could pluck the string, getting the kind of slowly decaying frequencies we've just looked at. If I damp the strings, hit it with my finger, you still hear a noise, but it dies away rather quickly. All instruments do that. When you pluck a string, you pull the string to one side, but that also puts a force on the body. And when you let go of the string, you let go of the body as well. So there's a sort of thump at the beginning of the sound as the body modes are excited. And in the guitar, you can see a little bit at rather low frequencies. In the banjo, there's much more of a spread of, there's stuff going on right up into the low kilohertz here. It looks like flames at the bottom. That'll turn out to be important in a bit. So that's a very first measurement. The next thing, I said that those measurements show that the banjo is louder. Well, of course, I cheated. What I showed is that they had more decibels when I measured it in some way. Is that the same as loudness? It's related, it's not quite the same. Loudness is a perceptual quality. It's not, to get something which really is related to loudness from measurement, you have to talk to Brian Moore first, and he lends you his software for doing time varying loudness. And that's what we've got here. So what I've done with the same notes, what I've now done is plucked every fret up to the 12th fret on this string on the guitar and on the banjo. And I've run them through this loudness processing software of Brian's. So to produce these kind of graphs of, this is the short-term time varying loudness, in that for those working in this sort of business, in this funny unit called Sones. Don't ask me exactly what it means. Read Brian's book. It's the definitive source on this. This is a perceptually significant measure of loudness. So I've done that for the bottom octave on the top string of both instruments, the solid lines of the banjo, the dashed lines of the guitar, and very satisfyingly, straight away they look different. Way up here, all the banjo notes are much louder, significantly louder, well beyond the level of what can be heard. They vary a little bit. That may be partly physics and partly the way I played the notes, but they're all up here and the guitar notes are all down here. So the banjo starts louder, but it also decays faster. You can see that in here. These decay rates are quicker. The guitar isn't so loud at the beginning, but it goes on for longer. Now I've only plotted this for 600 milliseconds, about half a second. The spectrograms over here have got 1.5 seconds. If we'd extended this loudness plot for longer, you would have seen that eventually the banjo, because it decays away faster, would end up being less loud. The guitar in the long tail of the decay takes over from the banjo as being louder. So that's our first little bit of evidence that really we should perceive these notes as being different. But loudness is pretty crude. We want to do more than that. And we can do one more thing with these same sonograms that we're looking at here. So given a sonogram like this one here, it's rather easy in the computer to detect these vertical stripes here. And you can take each one of those. I can take a sort of section through it, and I can ask the computer to fit a frequency and a decay rate. So from this one plucked note here, I would get the frequency and decay rate of the fundamental, but also the second, third, fourth, fifth, sixth, seventh, and so overtones. We can do the same for the guitar and for the banjo. We can do it for all the notes that I plucked. And you can put those together and you get this complicated picture here, which I will talk you through a bit, but we'll come back to this later. Now then, what have we got here? This is frequency along the bottom and loss factor up here. Loss factor is a measure of decay rate. Sorry, the banjo is ringing on me. I'm just putting it further away. This is the measure of decay rate on a logarithmic scale, and for those that are tuned into these things, a very wide logarithmic scale. There's a factor of 3 or 4 orders of magnitude here. There are big variations in this loss factor. So I do the thing I just said. We take one of those stripes in the sonogram, I fit something to it, that gives me a frequency and a decay rate, and that means I can plot one symbol on this plot at a certain frequency and a certain decay rate. That's the idea. Then we do it for all the overtones of each note and for all the notes we've played and for the banjo and the guitar, and you get this cloud of points here. The black ones are the guitar, the red ones are the banjo. Now, so we'll talk through the details of this plot a little later, but I'll just tell you a couple of things about it. There's some housekeeping stuff on here. All these sloping lines are simply lines of constant decay time in milliseconds. The loss factor is, that doesn't matter, they're constant decay time. The green ones are just a convenient guide so that I can look at one of these points and say, how quickly did that decay? The magenta line is the limit of the method I've used to process these. I simply can't find any points that lie significantly above that line. So all this white space up at the top here is not data, it's just the fact that I couldn't measure anything. And there probably is stuff in there, I couldn't measure it by this method, right? So there's no significance to that white space. What is this showing? Well, I'm only going to say one thing about it now, and we'll do it in some detail later. Look, ignore the red points, look at the black points for the guitar. And what you see is there's a cloud of black points up here, roughly where I've put this ring, and another cloud of black points down here for these low, and at least lowish frequencies up to a 2 kilohertz or so. Those are quite separate. I mean, really quite separate. These things have all got a loss factor in this range that corresponds to a Q factor, for those who think about these things, of about 30. And those are the modes of the body. That's the thump noise when I tapped the lute. Down here, then there's a lot of empty space, no black points to speak of in the middle. Then there's a whole cluster of things down around 10 to the -3, a Q factor of 1,000, long ringing notes. And those are the string modes ringing on for ages. So we're seeing for the guitar a clear separation of body modes and string modes. Up here, the black points and the red points look a bit similar. Down here, the black points and the red points are in different places in the plot, and that's going to tell us something interesting in a bit. We'll come back to that after we've got some theoretical models to compare it with. But let's turn to a different measurement. So this is the classic lab measurement. If you're going to do just one measurement on a plucked instrument, this is the one to do. What we call the bridge admittance. Remember what I said about the purpose of having a wooden box or a banjo membrane on your instrument. The string vibrates, the forces from the vibrating string act at the bridge. That makes the body vibrate, the vibrating body makes sound. This admittance at the bridge is the frequency response function at the bridge. So I choose a point on the string, on the bridge, for example, where this top string meets the bridge. I apply a force there by hitting it with a little hammer, and I measure the motion right at the same point using a laser system, preferably. And you can see various pictures of that on the right here. Here's a banjo, it's actually a different one, but that doesn't really matter. Here's the little miniature hammer. Here's a close-up of that, the little miniature hammer. This bright red spot next to it is where the laser beam is hitting. And so we're measuring, we're applying a force at that point, clonk with the hammer. The computer is grabbing the response. We do magic stuff in the computer, and we can turn it into these various wiggly lines that you see on the left here. This is velocity per unit force, but it varies with frequency. All these curves, I'll say what they are in a moment, are peaky. Peaks in this curve mean you get a lot of motion for a given amount of force, so that's a resonance. Low levels mean you don't get much motion for a given level of force, so those are in between the resonances. Now, what have we got here? 3 curves. 3 curves for 2 instruments, which I will explain. The black curve is the guitar. It's not the one in the photograph, but it's a similar, wouldn't have been very different if it had been the one in the photograph. What you see here is that low frequencies, you get a few large peaks. That's the guitar equivalent of the signature modes that Colin was talking about. But once you get above about 500 hertz, it settles down into this sort of noodling along the bottom of my graph on the way I've plotted it here. The red curve is the banjo, measured exactly as you see it in this picture here, on the bridge near the top string. Remember, all that data I just showed you was for the top string. So this is the relevant measurement for that string. Now, what do we see? We see some resonances at low frequency. Down in this frequency range, it doesn't look so different from the guitar. The highest peak of the guitar is rather a similar height to this first peak on the banjo. Once we get up to this range, though, they're enormously different. These two, the red curve is right up here, the black curve is down here, and they're 20 or 30 decibels apart. That's a huge difference. That's very encouraging. I said we're doing the banjo because it's extreme, and that's the first clear evidence that it's extreme. That's going to make a big difference to the sound of things. What's the blue curve? The blue curve is something I could do on the banjo and not on the guitar. I wouldn't have been thanked by my son if I'd taken the bridge off the guitar. It's the kind of guitar that has its bridge glued on. The banjo has a floating bridge like a violin. So it's actually rather easy to take the strings and the bridge off. And then I've hit with my hammer straight on the drum skin, on the membrane, at the same place where the bridge was before I took it off. And this blue dashed curve is the bare head of the banjo. And you can see that it's as high above the red curve as the red curve was above the black curve. Taking the bridge off the banjo makes an enormous difference. And that's going to be a significant thing in due course. So we have some measurements, and we will in due course use exactly these measurements to make some sounds, but not straight away. Here's some nice movies for you to watch. While we had the banjo in the lab, we did a scan over it with our magic scanning laser system. And these are just animations of some of the mode shapes. For purists, these are more or less mode shapes. They're technically called operating deflection shapes. Now, this is the lowest mode of the banjo head, doing pretty much what you would have guessed, the simplest possible thing. Second mode of the banjo head, third mode of the banjo head. But after that, I've just selected a few pretty ones from higher up, showing the very typical pattern of any vibrating structure. The lowest modes have the longest wavelengths and do the simplest thing you can imagine. The higher you go in frequency, the shorter the wavelength gets. More and more wiggles. So, now start pulling apart. We've seen that the banjo looks really different in that admittance measurement. Why? What's different about it? Well, the first thing is something that every violin maker would think of straight away. You worry about the mass of your top plate. Well, the mass of a banjo head, just the membrane, is about 1/10 of the mass of a guitar top plate. So it's simply very, very light. That's one of the important factors. Because it's under tension like a drum head, it can still withstand the down-bearing force of the strings, but it is much less massive. That's going to be important, but it's not the only thing. You can see there's some white space here. Now, the second thing is a rather technical thing, but bear with me because it's going to be important. Something called the modal density. Now, what does modal density mean? It means the density of resonances along the frequency axis. It's the inverse of the spacing between one mode and the next, right? It's the spacing. Now, membranes and plates, so any wooden instrument is basically a bending plate on its top. Any plate system behaves in essentially the same way. The individual mode frequencies, of course, vary with the material and the shape and the thickness. but this pattern of density is the same for any plate, which is that on average, the spacing of modes is constant. The individuals are all over the place, but you count the number within a 1 kilohertz band or something, and you get roughly the same number across the whole range. For a membrane, it isn't. For a membrane, the density goes up with frequency. So as you go to higher frequencies, you get more and more and more modes crowding in. And that's responsible for the difference of this trend here. Now, oh yes, now we can, right, remembering what my slides show, I can illustrate that with a super idealized example in the computer. Now, it just happens that if we choose a rectangular plate and a rectangular membrane, those are two textbook cases that we teach our undergraduates and where you can do it by hand. So I don't have to do any heavyweight computing. So the red curve is the head of a square banjo. I shall come back to the square banjo model later. And what I've done with that, so it's not the shape of a banjo, but I have given it the right area and the right tension and the right mass to match the real banjo head. And I've arranged that this first peak here matches the actual measured first peak, which is this blue dashed one here. It should be the same frequency, the same height, the same Q factor. So I've normalized things so that we match that aspect. Now the red curve here is then a version of what the square banjo in the computer behaves like. The black curve is a sort of guitar on steroids. It's a plate, it's a rectangular plate, not a very guitar-shaped thing, but I've made it the same as the banjo head in everything except that it's a plate rather than a membrane. I've given it the same mass as the banjo head, 1/10 of the mass. You wouldn't like to make a guitar this thin. This is less than paper thin. And I've arranged things so that I've made this first resonance in the membrane and the plate exactly the same. Same frequency, same height, same damping. So if you just compare the red curve with the black curve, you straight away see the effect of only changing this modal spacing behavior. The banjo, the square banjo has lots of modes. The plate has rather sparse modes. And the rather sparse modes automatically, for a reason that I'm not going to explain now, mean that the typical level is lower. But this was a plate on steroids. I already said the real guitar plate is something like 10 times heavier, and that's the dashed line. I might take this solid black line, but just make it 10 times heavier. All it does in this diagram is shift it down by 20 dBs. Now this dashed black line here is generically, we got the same vertical scale here as the measurements. The dashed black line is not so very different from the solid black line here. Individual resonance is not supposed to be matched, but the levels are rather similar. And the red curve is in the same general area of the plot as the dashed blue curve, which is what it was supposed to be. So in this really simple model, we're capturing one aspect of this really striking difference, the bare membrane being 40 or 50 decibels above the plate. And that's a combination of the mass and the fact that a membrane has a lot more modes. Right, back to this list. A third thing on the list. So I've talked about mass, we've talked about modal density, modal spacing. Now, the purpose of any sound box is to radiate sound. It's the only reason we've got it. Well, there's a really important difference between membranes and plates in the way they radiate sound. And it's something which catches people by surprise, because plenty of people, certainly in where I work, people think they know about sound radiation by vibrating structures. The world is full of engineering structures that make noise. Usually it's a nuisance. In musical instruments, it's desirable, but the physics is the same in both cases. So there's loads and loads of literature about how those systems radiate sound. But you think around the world, how many structures can you think of that make noises that are membranes? They're nearly all plates or curved plates. So 99.99% of the scientific literature on sound radiation is about plates. So when people say, oh, we know all about sound radiation, actually what they're thinking is that they know all about sound radiation from plates. Plates behave in a very particular way. Now then, the reason for this, so if we have a plate, imaginary plate in my hand, and a wave traveling along it, a bending wave, that will have some speed. And what happens in a plate is that the speed changes with frequency. Low frequencies, long wavelengths travel rather slowly. And as you go to higher and higher frequencies, shorter and shorter wavelengths, the waves travel faster in the plate. Right, so the wave speed starts slow and keeps on getting faster and faster and faster. Now, sound in air has a speed, the speed of sound, 320 odd meters per second. So for the plate, the speed of waves is going up, and somewhere it crosses the speed of sound. And that's called the critical frequency of the plate. And what happens to sound radiation in a plate is that below that critical frequency, it doesn't radiate sound very well. And once you reach the critical frequency and get above it, it radiates sound really well. So it's the sort of thing you use for designing your double glazing and things like that. Now, a membrane could not be more different. A membrane behaves like a string or like sound waves in air. There is a speed that waves travel on the membrane, and it's the same for all frequencies. And you put in some numbers because I know the tension of my membrane and I know the mass. So for any realistic membrane you can make out of a mylar sheet without it exploding, the speed of waves on the membrane is always slower than the speed of sound. So that means for the membrane, waves on the structure are always slower than the sound speed. But there is no critical frequency, they're always slower. So what that means is that for those high modes on the membrane with lots and lots of little wiggles, well, if you've got enough little wiggles, maybe the membrane almost thinks it's like an infinite membrane. An infinitely big membrane can't radiate sound at all. That's what this theory says, because the waves are subsonic. High frequencies on, high modes on my actual banjo membrane will be rather like that. Loads and loads of little wiggles, and the airflow just gets kind of cancelled out between each region and the next one, and it doesn't make very much sound. But the first few modes, remember the lowest mode on the membrane, it was just all going up and down. No wiggles, nothing to cancel with. So the finite size of a real banjo or a real drum means that the low modes do manage to radiate sound. But the more wiggles they get, the less good they are at radiating sound. So what that means that for the membrane, the sound radiation is good at low frequencies and gets less good as you go up. That's the exact opposite trend from the plate. The plate is poor at low frequencies and gets better as you go up. So completely opposite trends. That's the prediction. Is it true? Easy to do a measurement for that. So this is my claim that for a membrane, the radiation damping goes down with frequency. Well, here's some measurements on a banjo. This is simply taking a banjo, damping the strings, tapping the head, making that sort of rather drum-like noise. Then I process it in the computer in exactly the same way that I described earlier. We can find a frequency and a decay rate. So all the blue, I forget which is which, it doesn't really matter. The blue points and the red points are two different banjos measured like that. And there's a cloud of points and there's some scatter, but there's a really obvious trend downwards in frequency for this loss factor, this rather high loss into sound at low frequencies, getting less good. The green ones are the result of putting the strings and the bridge back on, and there's still a falling trend, although the actual value of the loss factor has gone up. That's another story. These red and blue ones make the point that I wanted to say. So that's the third thing that makes our banjo behave differently. Here's a little bit of direct data on that. Here, the makers will like this. This is just measurements on a banjo. Now then, David Politzer, remember him back at the beginning, so he got all this. He's a banjo nut. He's got, you can see I've got a certain number of instruments hanging on the wall behind me, but none of them are banjos. You get the same picture when talking to him, and the room is full of banjos. He's got lots of things. And in among his collection of banjos was one where you could easily change the head tension. So these are just some measurements where he's taken the same banjo, tapped it like I just did, and then raised the tension. Just look at this lowest mode here. Of course, the frequency goes up as you make the head tighter. But if you look at the width of these, you can see that the bandwidth of that resonance also increases. And that's the sound radiation getting more effective with a tighter membrane, something banjo players know about but didn't understand the physics of. And the reason for that is simply that as you make the membrane tighter, you raise the wave speed, so it gets closer to the speed of sound. It's still lower, but it's not so much lower, and it radiates better. As much as we're going to say. I want to get to the sound demos before we run out of time. So never mind about models. Let me show you, well, let me show you one thing. Hossein Mansour, you saw him earlier. I called him, he's an ex-student of mine, works for a software company that does wonderful software for computing vibrations. So I called in a favor from him, and he did some modeling on our banjo head to compare various things. And the most interesting thing that model reveals is on this slide. Now the red curve here, that's the measurement you've already seen, the bridge admittance of the banjo. The blue curve is his version of doing that in the computer. Not bad, pretty good match. But now something I'd already noticed in the measurement was where this vertical black line is here, there's a funny feature. There's a sudden jump in the behavior. And I thought that was probably a real thing, but I couldn't guess what it was. The computer model catches it rather well. And of course, in the computer, we can ask, okay, what's happening there? And this is a picture, exaggerated scale, of course, from Hossein's computer model of what's happening at that frequency. And we've got a kind of funny resonance of this little three-footed bridge that the banjo has. And it's somehow, the feet are all wiggling in a way that fits in with the wavelength on the membrane. So it's a kind of bridge plus membrane resonance, producing a little hump. Or if you do a different measurement on the bridge, you get a rather big hump. And this is directly analogous to the bridge hill on the violin, which I think most of you have probably heard of. There's a resonance associated with the bridge plus the stuff that the bridge feet are resting on, and it produces an enhanced region in some range of frequency, a sort of formant. But you can see there's some white space, and it says 2 bridge hills because that isn't the only one. If you measure this was measuring on the bridge at the top string position. If instead you measure on the middle, on the center string position, then you see another feature at a higher frequency. This one's about 5 kilohertz. The first one was about 3 kilohertz. Again, Hossein can show us what's going on, and it's a bending resonance of the bridge. So banjos have bridge hills, analogous to the violin, different in detail, but similar in principle. So that was an interesting discovery. But I want to get on to playing you some sounds. So never mind how. Given the bridge admittance, either from a measurement directly or from a theoretical model, plus knowledge of the strings, I think I saw Fantau on the list. Good string manufacturers will tell you things like the gauge of strings and tensions and so on. Otherwise, you can measure them. So if I know information about the strings plus the body, I can stir stuff in the computer and produce some sound files. We can either use that to listen to, or we can use it to compare with measurements. Now I'm watching the time here, and let's get to the, let me skip over this bit with the measurements and play you some sounds. Now, every sound you're going to hear is synthesized in the computer. No real banjo players were harmed in making these sounds. You're going to hear someone do a thumbs up. Did that come through all right? Audio quality, thank you. It's a little purely synthetic. I'll play it once more. And you ask yourself, would I immediately nail that as a banjo? I think it's quite banjo-ish. I think it's quite reassuring. Now so I'm going to play you some more sounds on the next slide. We can do two things. I can do things directly based on measurements, or we can use that square banjo model that I talked about earlier, where I can vary all the parameters. Then we can do virtual experiments. Now, the kind of virtual experiments Colin was doing, except that we're going to make sounds with them. So let me just play you some examples. But for technical reasons, I have to quit out of PowerPoint and show this directly. So here's the one you've already heard. That's based on that measurement that I showed you. I just showed you a measurement done at the center of the bridge, and that looked different. Here's the sound you get if you use the bridge center. Back. Really different. And that's just two positions on the bridge on the real banjo. Now, if I take my banjo strings and I do a virtual experiment, if I, instead of using the banjo admittance, I use the measured admittance on the guitar, you get something really quite different, somewhat guitar-y. And then because you're here, I could put a violin bridge measurement in instead. So here's what you would, this is the banjo violin. I just invented this. So this would be a banjo neck and strings, but driving a violin bridge in the bowing direction. Kind of interesting. A lot of people listen to that and say it sounds rather harpsichordy, and that would go back to my question about what governs the character of instruments. And that's a story for another day. But let me just, while the going is good, let me just play you a few other things. A quick one. Now, banjo players, just like violinists, may use a mute. They may change the mass of the bridge. That's a thing we can easily do in the computer. Furthermore, you've already seen in those measurements earlier that taking the bridge right off, so removing the bridge mass altogether, makes a huge difference. So here I'm going to play you synthesized sounds with no bridge, with the normal bridge, and then with a 5-gram mute added. No bridge. Regular bridge. And a mute. Rings on for longer because the energy can't leak into the body so much. I'm going to play you one more set of sounds here and then show one more slide, and I should just about get in under the wire for the end. I talked about string modes and body modes. By doing the right thing in the computer, we can separate those in the synthesis. So I'm going to play you a synthesized sound that'll sound just like the ones you've heard, but then I'm going to play you the string modes only and the body modes only, where the two added together would be the first sound. So here's the actual total. Here's the string modes. You have to listen rather carefully to detect the difference, but here's the body modes only. You can't, you hear something. Now the loudness levels are correct here. I'm going to show you on the next slide. So I've just got to avoid a pitfall here. What's going on there? There's something significant here. Here's a sonogram of that little tune fragment you've just heard. Here's the whole thing. Remember, time running up. Each of these horizontal lines is me or the computer playing the next note, da 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 da, and then they ring on. These are the string modes only. And this is that funny plinky noise of the body modes only. And now remember right back at the beginning when I first showed spectrogram measurements from the guitar and the banjo, and there was a lot more stuff going on at early times in the banjo note. The body modes, because of this super lightweight body and rather strongly coupled to the string, the body modes are a much bigger component of the sound. You can hear them for a guitar note once you tune into it, but in the banjo they're important. And I think this makes the point. This typical banjo music has this sort of forest of notes that come thick and fast. Now these body modes, you see them here, they do decay fairly quickly, but they're still going when the next note comes. These body modes are, you can hear this, these make a significant difference to the sound that you hear. If you don't have them in, it sounds rather bland and not very convincing to a banjo player. The body modes play a significant, this direct perception, even though you couldn't hear the tune being played when you listen to them, but they're a component of banjo sound. So let me proceed into my wrap up before Claudia starts knocking me on the head. So what do I think makes a banjo distinctive? Rapid decaying notes and loud. We saw that directly in data. The balance across frequencies is different because the banjo head has a lot more modes at high frequency, this modal density business. It has the thing I've just showed you. There's this initial clonk from this body mode transient response. And if you do it without that and play it to banjo nuts, they will say, oh, that's not really, there's something missing here. It's not lively, it's not, so that you can hear this. Banjos have bridge hills, that was a surprise. Now, just as all you violin people will know that adjusting that hill bridge feature, bridge adjustment is a key aspect of tonal adjustment, mainly because you're moving around one or more of these formants up with the bridge. The same is true with the banjo. Banjo people have much the same kind of folklore. You can buy all kinds of different shaped bridges. People will tinker with them. What they're doing is changing those two formant hills. It's sensitive to changes. I didn't talk about that. Let me just go to my very last sound, my very last slide. Where do I think we are? I claim that we've done not too badly on capturing the banjo, not banjo distinction. I think remember that one, the synthesis with the banjo response compared with the one where I put a guitar admittance in. The guitar one may not have sounded much like a guitar, but it certainly didn't sound like a banjo. The banjo ones sound reasonably recognizable. We can use the models to probe the effects of parametric changes all the way through to listening to them, like that one with the mute. I've got loads and loads of things like this. Anyone's interested, contact me offline and I can point you to a million other sound files you can listen to. And mostly, if you ask people, is this the kind of change you expect when you change the head tension or add mass to the bridge or whatever? Mostly they're reasonably credible, encouraging. So what about my original question? What about other stringed instruments? We can sort of recognize banjo-ness. Can we recognize guitariness or harpiness? Well, I'm still interested in that question, and maybe I'll talk to you again about that in some time in the future. And that's it. Thank you very much. Has that put me back to Claudia?
Yes, thank you very much, Jim.
In charge, more or less on time.
Yes, perfect. If there are people from my lab who want to ask a question, I'll give them the priority so they can leave afterwards. I can't see anyone raising their hands. I've lost the participant. Okay, let me check. Anybody raising their hands?
Andrew has a hand up.
Yeah.
One mute.
I was just whether there was some.
I'll jump in if nobody else is going to.
Yeah,
Can you hear me?
Yes, I think you can, because I don't see any other raised hands. So,
Claudia, I don't mean to be greedy.
No, nobody else says. I have a question as well, but then after you. Go.
Okay. Sorry, what's the difference between can you describe the difference between a membrane and a plate? What would you scientifically say is the distinction? What makes a plate and what makes a membrane a membrane?
The mathematician's answer is that one has a second order equation and one has a fourth order equation governing it. That's probably not what you wanted to know. The physics is different. If you think of a string, it's the same as the difference between a string and a xylophone bar. The vibration in a string, the restoring force comes from the tension. You pull the string to one side and the tension wants to pull it back. Whereas there's no tension in a xylophone bar. What it doesn't like is being bent. So you bend it and it wants to straighten. A plate is a two-dimensional bar, a membrane is a two-dimensional string. So it's that difference between restoring force governed by tension and restoring force governed by bending stiffness.
Great, okay, perfect. And thank you. I'll leave any other questions for later. Thanks.
Okay.
Perfect.
There is a question in the chat, Jim. Somebody who doesn't have access to a microphone. So he would like to know, if I bowed the banjo, what kind of sounds?
Wolfy is the short answer. It would have wolf notes, I'm quite sure. It's too lively. The peaks are too high. I've never tried it. You can bow a guitar with a little bit of effort. The trick is to thread the bow through the sound hole and use the tip of the bow to bow vertically, if you've never tried that.
Well, you could actually. You have a banjo with you, and I'm sure you have a bow somewhere.
There's no hole. You see, you need to bow it. There's another story, but
yes.
The component of string motion that's making the sound is the vertical component, and you can't get your bow in.
No,
because there's no hole. In the guitar, you can poke the tip through the hole and bow it vertically. So it would need, really hard. I wouldn't like to make a membrane with a hole in it. I think it would explode. So you'd have to do, no, you actually, right. We have some Chinese people in the audience. They already know what this sounds like. The Chinese have an instrument called the erhu. I think they may have more than one thing, which has a small body with a stretched membrane, traditionally a snake skin, and two strings, and you thread your bow in between the two strings. So look up the erhu on ERHU. Look that up on Wikipedia, and I'm quite sure it will play you some sounds. So that's a kind of bowed banjo. They must take some effort to make them not too wolfy. Anders Bowen has said, is the more loudness software open access? Send me an email to ask that. I can't remember is the answer. I'm sure he doesn't mind. And he gave me a link. I think it is open access, but
at some point it was on his website, but then the link was not working anymore. And so I don't know if
I think it's in MATLAB. I think it's on his research group website, but
and there are plenty of available options in MATLAB. People have coded it in MATLAB. So if you check like time varying loudness, you will get things for MATLAB. I think there are even some toolbox, loudness toolbox or something like this for MATLAB. Before I let Dmitry Tarakanov asking his question, I would like to ask my question because it's a bit related. I mean, when you did the synthesis with the guitar, you said it doesn't really sound like a banjo. Well, for me, there were still some of the characteristics of the banjo. So what is this due to? Is the string properties?
Well, I think mainly it was the fact that I was still playing banjo music. I think quite a lot of, can you recognize harpiness? Well, yes, you can as soon as people play a glissando across all the strings, because you can only do that on a harp-like instrument. So the music you choose to play gives a big clue. It's not all to do with the sound. If you just do individual one note at a time, it gets surprisingly hard to recognize instruments. Well, you of all people know that perception is subtle and multidimensional. So I do think there's the fact that it was sounding like banjo music is still relevant.
But I still heard like kind of almost like this metallic sound, which I think is very specific to the banjo sound. And I could still hear it even when it was filtered through the...
A little, although still,
we
could get the synthesized sounds we did for that guitar backwood project. Not so, that was a steel string guitar. I'm usually used to listening to classical guitars and nylon strings, but so just the metal strings and this very sharp pluck move you in that direction. The main thing you hear with the top string of the guitar versus the top string of the banjo is just that it rings on much longer on the guitar, and we more or less captured that reasonably well. But absolutely, I'm not claiming we've done everything. I'm claiming we've made a useful start. There's all sorts of interesting perceptual projects. Now, I would love you to get your group involved in this question of what gives instruments their characteristic voice, which things can be distinguished, how many dimensions does that perceptual space have? I think there's a really interesting question in there.
Yes, and then we have just started a project with Romain about guitar. So there will be more to come in due course. So Dimitri, would you like to ask your question? Unmute your microphone, turn on your camera.
Yes. Thank you very much, Jim, for a great talk. The really nice thing was about the bridge heels on the banjo and about checking the body modes of the body actually without the bridge. I don't think that's something body makers usually do, but maybe it can help with bridge tuning if we can check the body modes not from the bridge, not on the bridge corner, but actually tapping the body at the place of the bridge, and maybe it will answer to what frequency to tune the bridge to enhance our particular things. And my question was, can you tell a bit, please, about the software where you can adjust the properties of the instrument and synthesize the sounds that will actually produce?
Yeah, this is, I've done projects in the past on guitars and lutes, so I already had handy software for taking a little fragment of music and putting in string and body specifications, and it was easy to convert that to the banjo. So it's written in MATLAB. If you have access to MATLAB and would like it, I'm quite happy to send copies, but it's MATLAB is good if you are in an institution that has a license. If you've got to pay for it, it's not so good. So if you're the least bit interested in MATLAB codes, send me an email offline and we can have an offline conversation about that. It's, yeah, because I've got loads of other sound examples of different, variations among guitars. I mean, we did a project, Claudia was involved on the edges of it, a series of student projects on the thresholds of perception for moving individual resonances in a guitar body, that kind of thing. And we did all of that with the same software. It just makes it really easy to make a control change that would be hard to do with woodwork.
Cool, thank you very much.
Yes, there's stuff going on in the chat, which I'm...
Yes, so there is a question. A soundboard of a guitar bends more across the fibers than along the more rigid winter growth. That's not the case with the membrane. Does that change a lot the type of behavior of the vibration?
Yeah, it changes the details. I guess it's arguably, it may be the reason why banjos are circular, whereas everything based on spruce or something similar tends to have this kind of 2-to-1 ratio. Roughly speaking, the bending wave speeds in the two directions differ by about a factor of 2. So lots of instrument makers in different contexts seem to have gone to a proportion which is sort of effectively circular or effectively square. I don't know if that is really significant, but it is a fact, an empirical fact. The banjo is the same in all directions, and they choose to be actually circular. So that's a maybe. I don't know. It doesn't make a really big difference, actually. And people have made guitar bodies out of all kinds of materials. And as long as damping is in roughly the same range as wood, and as long as you arrange to get the first few resonances in roughly the usual place, they all sound remarkably like guitars. People have used plastic bottles and composite materials of various kinds, and you can use all kinds of things. Some of them are isotropic and some of them are not. It moves all the individual resonances around. It doesn't change these kind of high frequency spacing statistics that I was talking about, but it does change your signature modes. Your low modes are sensitive to everything, material, shape, holes, everything. Once you get up to high frequencies, almost none of those things matter all that much. Well, only a few things matter. It's only these sort of statistical things. You can't tune individual resonances in any instrument at 5 kilohertz. What you can do is adjust formant-like features like the bridge hill in the violin or the banjo. There's some stuff going on in chat. But
yeah, it's hard to follow everything.
I've never tried the thing in octave, just Anders. Yeah, okay. Tim's saying he's going to talk about isotropic versus anisotropic on Thursday, so you get an answer for that.
And then Roma said as well that because it's not because the behavior is different that you have less waves traveling on one direction than in the other direction. It's more like...
Yeah, I think that if you try to dig into what exactly that means, it fades away before your eyes, and I'm not sure that I could put a definite meaning. So I think it's, I'm sure you're trying to convey something which is right, but seen through the eyes of a scientist, I'm not at all sure what you mean there. I mean, in the end, the plate is moving a certain amount in a certain shape. That's, if you choose to express that in terms of waves traveling in different directions, then they're both in there. There's a famous thing in the literature. The people in Sweden who've done lots of stuff with optical measurements have done measurements on a violin where they essentially hit it with a hammer and have shown the transient waves spreading out. And there you can see that it is roughly the same amplitude in all directions. Dig those out. It's Janssen and the chap at Luleå who does the optics. I can't remember the reference offhand, but there are 2 or 3 papers from the Swedish people about transient response in violin tops, with these really rather nice laser pictures showing the wavefront spreading out from an impulse. Have a look at those.
Do they spread more along one direction than in the other direction?
They go faster. You see them going twice as fast one way as the other, but the fringe heights are pretty much the same. So the amplitude is pretty much the same in all directions, I think, from memory.
Okay, I think that's probably what
have a look.
Romain wanted to.
Yeah, they're easy to find, but I don't have them sitting here.
So Anders is asking, you say that banjo sounds need the body mode to sound natural. Is it the same for violins?
Well, I think so, and Claudia has never been convinced. In the guitar, the bowed instruments are different, right? And plucked instruments, you've always got this rather abrupt start to every note. And so in the guitar, you certainly do hear it, but it's just a small number of very low modes going thump, thump, thump every time, which you can learn to hear. Now, if you want to hear, they're certainly there in the violin. And indeed, if you were only interested in a pizzicato violin, then I'm sure the answer would be yes. In a bowed instrument, I think these things are important, but they're going to be more important. It'll depend how you bow it. If you play a martelet or something like that, a rather abrupt note start, then there's lots of scope for exciting those body modes, and maybe people hear them in some way. You do a gentle string crossing transient, then maybe the body doesn't notice in any very definite way. You need an abrupt transient in order for things to do. Colin is drowning or waving. Unmute yourself, Colin. You're muted, Colin.
I'm unmuting. You no longer. Can you hear me?
Yes.
I believe with Jim that the body mode sound is important for the violin as well. You can see it in some of my slides. There's a lot of body mode noise, even in the bowed string. And because it occurs over a wide frequency range, it's not so peaked like the main resonances. The brain is getting all that information, and it must be weighted rather more strongly. And even though it's a low amplitude, it's over a wide frequency range. And therefore, I think even though it's low, as in when you bow a note, I think that body mode sort of sounds is important.
Let me show you my trick. I've just pulled a violin off something I like to do when I'm listening to violins, people comparing violins. So if you have two violins that you think you can recognize different, do this. Hold it so you damp the strings, and then clunk on the corner of the bridge. Do that with your two violins. My claim is that if you can tell the instruments apart by playing, you may hear different sounds when you do that. And then more contentiously, maybe it's the same kind of difference. Now, Claudia is trying to do tests on this and never succeeded. I know that. I still think there's some truth in there. But it was,
right. No, I agree. There was a huge difference. And actually, I thought the differences between the violins were even more obvious with the clunks than they were while playing them. I mean, at least listening to them being played.
I recommend this to all. You must all be in the kind of business where you, from time to time, are comparing instruments, and just listen to that clonk noise and see if that does or doesn't. I'd be interested. Let me know if you find it always works for you. I'd be very interested to know. If it doesn't work, you keep quiet about it.
It's just like it's very hard to actually relate if you hire two different clonks and two different musical phrases, and you have to match which one is which. It's not that easy.
Oh, sure. Yeah, absolutely.
Any other question? I mean, you know, it's open for discussion. So if you want to ask questions to Colin that you were not able to ask before, feel free as well. Andrew.
Oops. Hello again. So these differences in the signature mode and the clonk noise, it's my sense that has to do with the power of the coupling or the quality of the couplings in the instrument.
The quality of the?
If you listen, the coupling, how well the instrument is coupled, how well the lowest modes are coupled. So,
coupled what? I mean, I think you're hearing those few signature modes, so it's how good they are at radiating sound and what their damping factor is.
Right, and that in my opinion, that difference is that how much noise is there in the coupling? So how efficient is the coupling? How well are they coupled? Are they is there a lot of destructive interference or a lot of additive interference? That's what the difference between a good violin and a bad violin is how well these modes are coupled, these lowest modes. in my opinion.
Yeah. Can you hear me?
Yes.
Yeah. Clearly, the coupling is very important to the sound. The better the coupling of the strings to or the banjo to the body, because it's the body is the thing that's radiating the sound, the more important, the stronger the coupling, the larger the sound will be from that sense. But the other thing is the very different sound that you get, of course, when you clonk it, as Jim was showing beautifully, is very different from the sound that you actually hear with the strings free. And when one's making, I've always felt that when one's making judgments of what an instrument sounds like, the sound that you actually get with from the damped strings is very different from that which you get when you undamp the strings. And yet everyone makes a comparison of measurements that are made with damped strings. Jim might like to comment.
Well, I'm in a strong position for putting my particular prejudice. If you want to do the kind of thing I was showing in my talk, where I've taken the behavior measured from the body of an instrument, banjo or whatever, and then used that to synthesize sounds, I wanted to be in charge of adding the strings in to play the music. I didn't want the body measurement to have the dynamics of the strings in. So I like to measure the body behavior with the strings certainly damped, but they've got to be there. You've got to hold the bridge in place. There are some more subtle things to do with the stiffening effect of the strings and the break angle and so on. But the resonances of the strings, including the after lengths, show up as undesirable features from the point of view of doing the kind of thing I was just doing. In the violin world, the equivalent thing, or violin family world, one of the things you can do with the bridge admittance there is produce some predictions of the propensity to wolf notes. And again, I don't want the string already there in the body measurement if I'm going to try different strings in the computer to say what would it do in terms of wolfiness. So from my particular scientific agenda, I definitely don't want the strings ringing. That's a different thing from saying if you want to do a measurement to capture the sound of a violin, whatever that means, then maybe you want it and maybe you don't, but there's a perfectly good argument. I mean, I understand where Colin is coming from. I mean, if you do my clonk without damping the strings, then you hear a lot of strings ringing on compared. I mean, the clonk is still the same. The banjo strings are also ringing in the background here.
Can I come in? Can you hear me?
Yeah.
Yeah. I mean, my viewpoint is that if one is trying to understand what the sound and the quality of go back to just a violin for the moment, is that if you want to judge what is actually making the sound of the violin, then you must actually have the ringing strings, because that gives the ringiness to the sound. And Claudia might not be happy with me talking about ringiness, but every time you talk to a professional musician and they're talking about the quality, it's the ringiness of the sound, which is one of the important elements that they judge the quality by. And therefore, if one's trying to assess the quality of the sound, that one must actually use to compare the sound with the strings undamped, as George Bissinger was a great advocate. And in that sense, I believe him. But I agree entirely with what Jim is saying. If you're going to synthesize sound, then you don't want that ringing, because you're going to put in the ringiness of the strings basically as part of your string sound, the actual sound. But I think I'm in a minority view, because I mean, almost everyone in the acoustics field follows Jim's type of model, using basically the information about the sound of an instrument with the strings damped.
Well, I've started taking both measurements.
Yeah, well, I think that is good. And actually, you can see, in fact, on the admittance or any other measurement you make, what you do is put on top of the admittance with strings damped, you just get the individual peaks of the various partials of the string that are being excited when you hit it with a hammer. But it's this is an essential feature, in my view, of the sound of an instrument.
Okay, there is Evan. Would you like to talk, Evan, instead of typing your question? Or do you want me to read it?
It really wasn't a question.
Or a comment? I can't follow.
Yeah.
I can't answer and read at the same time.
Hi, Colin.
Hi, Evan. Great to hear you, though I can't see you.
Yeah. So in doing the clunks, one of the things that I have done is record them on a number of different instruments and then modify the instrument. And then play this game that we all learned from Sesame Street. Which one of these is not like the others?
Yeah.
You'll have two that are the same. The third one is different. Can you hear that change? I've done this at Oberlin and other places, and most people can hear it. So it may be a way of educating yourself on this is the sound of a F-hole stuffed up, or this is the sound of a mute. Start with the big changes, like Jim said, something that's dramatic. Put a mute on the violin, you'll be able to hear it. How small a mute can you put on before you stop hearing it? So simple recorders and a little bit of which one of these things is not like the others is a very educational process. After Jim had showed me his thumb tap a number of years ago, I came home and bruised my thumb by tapping everything in the house, and I could tell the difference between instruments that I couldn't hear while playing. I could definitely hear it with the tap. So
yeah,
it's a tool.
Yeah, I agree.
Good, thanks. Hi, Evan.
Hi.
Okay, George would like to say something.
Yes. Can everybody, am I being heard?
Yes.
Yeah. About the damping of the strings and things. Obviously, when you're doing modal analysis, the strings ringing on are just a damn nuisance. That you have no chance of fitting modes if you leave those in. But another point really is that if on all instruments the strings are nominally the same. I know not every brand of string is identical, but they're all doing rather similar things. So if we talk about the property of ringiness, I think that really is something that ought to be visible in the analysis, in the admittance. So I think the argument of saying that you need the strings included in order to understand the sound is not really correct. That's just my point of view. I think it's in there. If one instrument is more ringy than another, somewhere it's got less damping. It's the same for all instruments nominally.
But the ringing actually comes from the ringing strings, and it's to the extent to which you've excited those strings that's important.
Yeah, so you're saying that if you're playing one string, you're exciting resonances in other strings. Yeah, but that must be something to do with the mobility of the bridge. Is it a property of the strings? I take the view, more Jim's view, that you can separate the two, and that you need to understand what's going on.
Okay.
Anders would like to comment on this as well.
Can you hear me?
Yeah.
Yeah. I was thinking about what Colin said about ringiness, and we Hardanger fiddle players or fiddling with Hardanger fiddles, we like reverberance, and I tried Colin's Viom some time ago, and it has a very ringy and nice E string, I think, and very nice, very seldom, and I think also at the VSA competition a couple of years ago, we are allowed to play the instruments, and the winner instrument there had a very ringy E string. That's one comment, a good thing about the instrument. And another one is that when you hold the instrument, you will damp it, and it's a different thing when you mount it in a vibration insulated system or rig, and when you hold it, and it can be quite a lot different. And I wonder, how does that influence the perception of the modes, and how has there been done any investigations into this for guitars and so on?
Can I comment?
Yes.
I will show some measurements of this on Wednesday morning, and holding an instrument, in fact, dampens down the main signature modes, but not the A0, but the B1 minus B1 plus by about 6 dB. But if you hold an instrument under your chin, that is the worst, particularly without a shoulder rest. But you can still play a violin held at the neck and play it out here. And under the ear, surprisingly, it doesn't actually seem to make very much difference in sound. But when you hold it like that by the neck, or just at the neck joint, it's almost like having a free violin, in fact, for the measurements. And I can do measurements with my measurements inside the violin very easily to show you that there's about a 6 dB effect that comes from holding it underneath your chin. So this is what worries me about, when you're trying to assess the difference in sound quality with small 2 dB, 3 dB changes in the low frequency response, where that simple test shows that it has a remarkably, under the ear, it has a remarkably little difference to the sound, and presumably also therefore in the radiated sound, though I've never done it. But there's a very strong correlation between the sound inside the violin and the radiated sound. So I feel sure it will be there in the radiated sound.